Now I'm going to review what standard error is. So remember, standard error was talked about when we were in phase 5 and 6. So for a one sample mean test, so for a Z or a T test, the standard error is the standard deviation for the sample means. So in other words, it tells us how much we would expect our sample mean to vary from the population mean just by chance. And we calculated by this formula. So we had standard error equals the standard deviation divided by the square root of n, and this was specifically for a t-test. If it was a z-test, we had the population standard deviation at the top, but I'm just going to show you the t-test for now. So again, the standard error is the standard deviation divided by the square root of n, and this gives you a measure of variability for the sample mean. So it's how much you expect your sample mean to vary from the population mean just by chance. Now in this phase, we're talking about dependent t-test and independent t-test. So for these two, we have a little bit of a different definition of standard error, but it's almost the same. It's just slightly different depending on the type of test. So for a dependent t-test, the standard error is the standard deviation for the sample mean of difference scores. So remember, for a dependent t-test, we have two columns and they're paired. We calculate a difference score column, and then we get the mean and the standard deviation for that difference score. So when you're talking about a dependent t-test, we're only concerned about the variation and the difference scores. So we make a column of different scores and then treat it as a one sample t-test. On the other hand, for an independent t-test, we have two different columns and we have two different means and two different standard deviations for both of those columns, right? They're not paired, so we can't do the difference scores. So instead, we have two different means and two different standard deviations for both of the columns, for both of the populations. So for that, for an independent t-test, the standard error is the standard deviation for the difference of sample means. So it's how much we expect the difference of the sample means to vary. Okay, just by chance. So to get the standard error for the dependent t-test, right, we make a column of different scores here, and then we find the mean and standard deviation of the different scores, and then it's just like a one sample t-test. So after you get this column of different scores here, we just ignore all this, ignore that, and then add all these different scores up and divide by the total to get the mean, and then go through all the steps to get the standard deviation just on the different score. So ignore the rest. And that's what I'm going to ask you to do on the next slide, is to get the standard deviation of the different scores. So now, after you get the standard deviation of the different scores, which we're going to denote by S subscript D, so this is the standard deviation of the different scores, we need to get the standard error. So the standard error is how much we expect the mean of the different scores to vary from sample to sample. So the top, that's just for the different scores. So how much do the individual different scores vary from each other. But the whole thing, the standard error, is how much you expect the mean of the different scores to vary from sample to sample. And you can notice that this formula is very similar to the one sample t-test, but we have the D's here. So we have the standard deviation of the different scores divided by the square root of the sample size for the different scores. And note that the sample size for the different scores is the number of pairs, not the individual observations. So it's the number of pairs, or the number of different scores that we have. And to get the degrees of freedom, we take the number of pairs minus 1, just like we would in a one sample t-test. Now I'm going to talk about the standard error for an independent t-test, and in order to do that, we first need to talk about the degrees of freedom for an independent t-test. So we're going to have two columns that we treat separately, right? And so then we're going to have two different types of degrees of freedom, one for the first column and one for the second column. And then we're going to have a degrees of freedom total, which is the total degrees of freedom. So it's the sum of the two degrees of freedom here. So for your first column, you have the degrees of freedom 1, which is your sample size for the first column minus 1. And then we have degrees of freedom 2, which is the number in your second column minus 1. So it's the number of observations in your second column minus 1. And then you add those two up to get the degrees of freedom total. Note that the N1 and N2 can be different. It doesn't have to be the same. So you can have 3 observations in your first column and 4 in your second column, and that's okay. For a paired t-test, you have to have the same amount of people in both columns, right, because they're paired together. But for an independent t-test, this doesn't have to be true. We can have 100 people in the first treatment group and 50 in the second treatment group. So the ends don't have to match, but a lot of times they do match. Also, before we talk about the standard error for an independent t-test, we have to calculate what's called the pooled standard deviation. The reason that we calculate the pooled standard deviation is because we're going to assume that the standard deviations for both of the populations, for both of the columns, but for the population, are equal to each other. So if they're equal to each other, then we can kind of aggregate them, put them together to get this average, and use that as our standard deviation. So there's another type of t-test that doesn't assume equal variance, but we won't discuss that in this class. The degrees of freedom are a little bit strange, and Excel can do it pretty easily for you, but we're not going to do it by hand in this class. So again, we're going to assume that the population variances are equal to each other, or the population standard deviations are equal to each other. Okay, but when we randomly select a sample, right, the standard deviations are going to vary a little bit from each other, and we're going to expect that the standard deviation with the highest sample size is going to be more accurate than the standard deviation with the lower sample size. So we're going to give more weight to the standard deviation with the higher sample size. So we're going to calculate what's called pooled variance, and basically it's just an average of the two standard deviations, but we're going to give more weight to the sample standard deviation that has the highest degrees of freedom. And if they have the highest degrees of freedom, that means it also has the highest sample size, right? Because it's n minus 1. So if you look at this formula, the top is the degrees of freedom for the first column times the variance for the first column. So if you have standard deviation here, then you need to square it to get the variance, and then it's the degrees of freedom for the second column times the variance for the second column. Okay? And then we divide by the degrees of freedom total to get average. So you have the two standard deviations here, the variances, and then you multiply it by the degrees of freedom. So whatever gets the higher degrees of freedom is going to have more weight. It's going to be, and when I mean by weight, it's going to have more influence on this pooled variance. So whichever sample has the highest degrees of freedom, this pooled variance will be closer to the standard deviation for that sample that has the highest degrees of freedom. So it's going to be closer to the standard deviation for the one with the highest degrees of freedom, okay? And it's going to give more weight to the one with the highest sample size because it has more information, so therefore we say it's more accurate. And we're going to assume that in the population, though, that they're equal to each other. It's just that the standard deviation with the higher n is more accurate. And so we're going to give more weight to it, okay? So after we get the pooled standard, or the pooled variance, we can also get the pooled standard deviation. And that's just the square root of the pooled variance. And again, more weight is given to the sample with more people. And a weighted average of the two, it's a weighted average of the two standard deviations. And we have two, but we only need one because we assume they are equal to each other in the population. The sample with the higher sample size is given more weight because it has more information. It has a higher n. So once you get the pooled standard deviation, right, we're aggregating or averaging out the two standard deviations to get a pooled standard deviation because we're assuming that in the population that they're equal to each other and that they're only different because of sampling error. So once we get the pooled standard deviation, we're going to use that to calculate the standard error for an independent t-test. And that equals the square root of the pooled variance divided by n for the first column plus the pooled variance divided by the n for the second column. And we want to double the variance because we are accounting for the variance of two sample means. So, you know, they're both going to vary on their own, and then we kind of double it, we add it together to get the variance for both. And if they're independent samples of each other, then to get the total variance, you add them together. Okay? Another formula that you can do is this one at the bottom here. And you can take the pooled standard deviation and multiply it by the square root of 1 over the n for the first column plus 1 over n for the second column. And these two are equivalent to each other. You'll get the same answer. So you can use either formula, whichever one you prefer. They'll give you the same answer.